Thank you guys for joining in time. And this is the only slide that I have, 7, 8 hardly. I want to make this more of an interactive session, more on coding, okay, so that we are able to actually see how neural networks work, okay. So let's get started. And I request the audience to put all your questions in the Q&A section only. I'll not be watching the chat box for your questions. If there is any generic networking that you want to do, please take the chat box, the webinar chat. But if you have technical questions related to the topic that I am discussing, I'll be only watching the Q&A section, right? Okay, so how many of you are completely new to neural networks? I mean, you might have just heard the name, but never done anything. So just give maybe a quick hand raise. I can have a count. Okay, I see 8, 9, 10. So it seems that a lot of people have already started working on neural networks already. Okay, and how many of you are slightly comfortable with neural networks? You might have done some project on neural networks, maybe CNN models, image classification, image detection, or object detection, object tracking, anything similar. Okay, so we have people who just have theoretical knowledge. Fine. Okay. YOLO. Okay, perfect. So we won't be going that far. Okay. Do not have any knowledge, second year student. Okay, let me do one thing. I'll just quickly check the YouTube section as well. Okay, perfect. So a lot of people have some exposure. So it's a mixed bag. That's what I get now. Mostly the audience is mixed bag. Okay, so people have already worked with TensorFlow and PyTorch. Okay, good. So we would not be, discussing about PyTorch because we have exactly 1 hour session from the point I start. Okay. And it's difficult to cover into or delve into too many things, okay, because I've already mentioned that this is going to be a beginner friendly session and I want to keep it that way. Okay, so let's get started. So I'll not invest too much time into the timelines just because neural networks is not something which came up in the last 5 years or 10 years, frankly. So this has been there. The concept of neural networks was formulated somewhere back in 1943 something. Okay, so you can always ask ChatGPT. So how many of you haven't yet used ChatGPT? Okay, let me put it this question. So the whole architecture, the backend of ChatGPT, the whole model, the backend model on which the ChatGPT has been trained, okay, is a neural network model. Okay. So a lot of application areas are there. IBM Watson is there, Alexa, AlphaGo. Okay. So these are already deployed applications. Yes, I'm watching the chat box as well. Okay. So the thing is, if you haven't yet tried ChatGPT, you should be trying that out because the backend is still all the neural networks. So of course, in this session, we would not be discussing about the architecture and we would not be able to go to that level definitely. But it is good to know that so whatever we are going to learn today is very much relevant. That's the point. So when I asked that question, the intention was to tell you that the concept of neural network has been there for more than 80, 90 years. Okay, it's not that neural network came into existence in the last 10, 15 years only. But neural network gained popularity in the last 10, 15 years. I would say. Okay. Now, why did it gain popularity? For the simple reason, training the neural networks requires a lot of memory, a lot of speed. It's computationally extensive. Okay, intensive, I would say, computationally pretty intensive. Okay, and you need that kind of processing power. So prior to the GPUs, the training of neural network used to take days, even on very high sophisticated GPUs, the training of very sophisticated neural networks do take days. They have been trained. There are a lot of pre-trained networks that we will probably talk in the next session. I have planned another follow-up session on pre-trained networks as well. Okay, so they have been trained on GPUs. Okay, so the thing is, prior to the advent of GPUs, training the neural network on CPUs. Think about the Pentium processors, okay, 386, 486, okay. Barely you can run some Windows applications, and using those processors, training a neural network is hell of a job. So neural network, when it is not trained properly, cannot perform a job. I mean, properly. That the reason never gained so popularity, and because another big reason, and that's the cloud. So with the cloud at hand, you can scale up your computational power. So let's say you want a 16 GB RAM or 160 GB RAM. You can add as many cores, add as many GPUs over the cloud, and you can use 160 cores or 320 cores also for your training process. Okay, so that's still very seamlessly possible, easily. Okay, so with the easy to the GPUs and cloud platforms, training of the neural networks have become very easy, and that is the reason why it has gained popularity. And now we have so deep neural networks with almost 175 billion parameters are there. We'll see the calculations of these parameters in this particular session, what these parameters mean. You might have heard this statement. This chat GPT-3 or GPT-3 has got 170 billion parameters, and now we have the GPT-4 version coming up, 230 billion parameters. So how do you train so many parameters, right? So that is the thing. So let's get started. I mean, I can give you a biological analogy first, and then how this biological neuron translates into an artificial neural network or artificial neuron. Basically, neuron is a building block, and network is basically when you connect all these neurons together so as to process the data, to learn the pattern in the data and give an output. That's called as neural network. So in our brain, we have, the brain is your main processing horse in your entire body, right? That processes all the signals which is coming from your five senses. Okay, so all the stimulus is passed to your brain in the form of electrical signals, and in the brain, these nerves carry forward these electrical signals to the brain. There in your brain, you have these neurons. So these neurons interact with each other and process those electrical signals and help us to identify the eyes, what they are seeing, the nose, what kind of smell it is, the tongue, what kind of taste it is. Okay, ears, what am I hearing, and if someone is pinching you, what kind of touch is that? Okay, so all that processing is done by these neurons. A single neuron does not process anything, big. Okay, I would say. So you need billions of these neurons in a proper networked way. Okay, so as to make sense out of these signals. That is the main thing, right? So dendrites is something which will these are the inputs to the neuron, I would say. So dendrites is something which is collecting the input from a previous layer of neuron, you can say, or from a previous neuron. So dendrite will connect with another neuron. So dendrite will take the input. Nucleus is something where the entire information is processed. Okay, the process information is passed through this axon, which is covered with a sheath and all. And these axon terminals are there. So you can see a lot of branching. So the same signal is passed to multiple neurons. Okay, so all those multiple neurons will again process the same signal, and then they will again pass the processed signal to another layer of neurons. That is how it goes. And that's exactly the same concept we follow in our artificial neural network also. So we have an input node, will have a processing, something like a nucleus, and then we'll have an output layer. Okay, so input node, a hidden layer which will process all the data, and an output layer. So at least three things we will have in our artificial neural network as well. Okay, so these are the main application areas. I would just go through them very fast because many of them are already known, but the point is fine. So computer vision, so basically image detection, image or object detection, image classification, object tracking. Okay, a lot of these applications which deal with. So just imagine you want to identify whether a given image is a cat image or a dog image, or a given image has got a person. Now, is that person Prashant or Donald Trump? I mean, so that kind of image can be classified whether this person is Prashant or no Prashant. That's a simple classification. You can identify the objects in a particular image. Okay, this object is a computer, this is a mouse, this is a printer. So different objects can be identified. So these are all separate application areas related to computer vision. And then you have natural language processing. So this is what the ChatGPT is all about. So language translation means you can translate text from one language to another language. So let's say I'm speaking in English, okay, and there is a real-time translation which can happen in Zoom in another language like French or German, okay, or any other language that you want to hear. So how do you translate text from one language to another language? For that, again, you are going to use neural network. Sentiment analysis. So this is like, I actually took 4 sessions on sentiment analysis before in the month of November, December, and Jan. So I don't know if anyone of present here have attended those sessions. So sentiment analysis is like given a product review or a movie review. Okay, you can try to identify whether that person was happy with that product or not. Okay, so it's a positive sentiment or a negative sentiment, or is it a neutral sentiment kind of thing. Speech recognition again. So given a voice data, okay, we can identify what this person is saying and who that person is. So there are 2 things you can do in speech recognition. Okay, so identifying the person is one application, and identifying what that person is saying is further another application. So all your speech to text converters like Google, okay, Alexa. So you are talking to Alexa, and Alexa is able to convert that spoken language into a text. That text is searched in the backend. So let's say you say, Alexa, play me a lullaby, okay, or play me so and so song. So how does Alexa able to perform that action? So it is able to recognize what you are saying, understand what you are saying, and then that text is searched over Google or maybe somewhere, and it searches and fetches the relevant information. So you are asking, what is the weather looking today? Okay, so it will give you the weather information, and then that text is spoken back to you. So that's another level of conversion. Okay, a conversion of speech back to text. So all that speech to text and text to speech. This is all going to use your neural networks. Text classification, it's like imagine your document classification. So whether this given document is a medical document, legal document, it's a invoice, or is it a receipt? Okay, so you can classify different pieces of documents. Robotics, you train robots, okay, motion planning, control, and all that. So have you seen videos of Boston Dynamics? Have you seen videos of Boston Dynamics? Okay, fine. And then finance, you can create a model which can predict the stock price tomorrow. So that's like a stock price prediction based on the historical data, based on the historical trend. Okay, so you feed 15 years of daily movement, and then you train your neural network. Okay, so your now neural network is able to identify the patterns, basically the most usual patterns, the candlestick patterns. That's one way of doing technical analysis. Otherwise, if you don't want to learn technical analysis, let all the technical analysis be learned by your neural network. Your neural network is sophisticated enough to learn all that analysis from historical data. So you need some good amount of historical data to be able to train your neural networks. That is one drawback of the neural networks also. If you use less data, the accuracy of the neural network would be actually worse than a simple machine learning model. Let me warn you that way. Okay, that is how a neural network has cons as well. It's not just having pros, it has cons as well. So training the neural network, I have already mentioned, is a computationally expensive, intensive process. That's one cons. Second, I said the data requirement for the same application will be at least 10x. So if you have 10,000 data points, you can make a machine learning model very easily. You will be able to get 90-95% accuracy. But if you use the same 10,000 data points for a neural network, either you will need a very sophisticated neural network. If you use a vanilla neural network, you might even get just 70% accuracy, right? So other option is increase the data volume and the data quality, right? And then so on. So a lot of applications. So we are done discussing this. Okay, so how does a neural network finally look like? Okay, so you will have basically at least two things. Some input nodes, as you can see here. What are the input nodes? So input nodes will capture input from your user, let's say. Right? You have a data set. You need to have a data set. So everyone here is aware of, let's say, iris data set. Is everyone aware of this iris data set? Come on, let me take it that way. I'll try to give you more practical examples, because if you are here directly without having a knowledge of machine learning or no exposure to data science, it will be difficult because I cannot explain those terms at all. Okay, that's much beyond the scope. So everyone here who has some background of data science or machine learning would have definitely encountered iris dataset. It has got 4 features. It has got 4 features. At this point, I would strongly recommend you to grab 2 things. Number 1, a pen and a paper, because my slides are pathetic, number 1, and I would be speaking a lot of things. And I would be repeating that at a pace that you are able to note it down. Because my slides will have just pictures. There would be rarely any text. Okay, so that it will not help you at all. Okay, so if you start noting, it will register in your mind immediately. Okay, 2 things. So if you are aware of the iris dataset, there are 4 features. One is sepal length, one is sepal width, one is petal length, and one is petal width. So there are 4 features, and that's the reason I have got 4 nodes in my input layer. So what is the first point to be noted? The first point to be noted is the input layer has got nodes. I did not say neurons. Please listen to me very, very carefully. Okay, I'm going to be technical now. Okay, this is one very thorough mistake most people do. If I simply ask you how many layers are there in this network, most people would say 2, which is thoroughly wrong. It's a single layer neural network. It's a single layer neural network. So you do not ever count the input layer as a neural network layer for a reason that it does not have neurons. What does the input layer have? The input layer has nodes. That is the first point. The input layer has nodes. Second question. What is the job of the nodes? The job of the nodes is to capture the inputs from your data set. Third question. How do I know how many nodes will I need? Answer is simple. The number of nodes in the input layer is exactly equal to the number of features in your data set. Is that very clear? Step by step. Is everyone following me? And this is how I will be going through the session. Like, it's going to be a straight away question answer sessions. You should be able to answer these questions if someone is saying, asking you. Okay. So first and foremost, once again, I would repeat, the input layer is never counted as a layer while counting the total number of layers in the neural network. Then I said, input layer does not have neurons. It only has nodes. Then I said, how many nodes would be needed in your input layer? That is exactly equal to the number of features in your data set. So you need to have a data set. You need to have a clear understanding of your data set. Of course, how many rows and columns? The number of columns is the number of features typically, and the number of features will determine the number of nodes in your input layer. Simple. The job of the nodes is to collect the values of the features. Perfect, perfect. And now I've got an output layer. Okay, so that output layer, if you see, has got 1 neuron. That output layer has got 1 neuron, right? What is the job of the neuron here? Okay, so the job of this neuron is to process the inputs. So all the inputs are coming from here, okay, and all the inputs are coming. And this guy processes all the inputs and gives an output. How is that processing done? That I'll tell you in the next slide. Okay, is that very simple till now? Now I'll show you another neural network. Okay, now it has got one additional layer. So how many layers are there in this neural network? Come on. How many neural networks are there in this neural network? 2, exactly. Don't make that mistake. It's 2-layer network. Perfect. Awesome. Awesome. So input layer is never counted. These green things are input nodes. I've got 5 neurons in my hidden layer. I've got 5 neurons in the hidden layer and the output layer. So what is the job of the neuron in the output layer? Question answers. So unless you are clear, okay. So what is the job of the neuron in the output layer? The job of the neuron output layer is to give you the final output. The output of the neuron will be the final output of your neuron. But someone has to learn the pattern in your data, right? Just imagine you are feeding those features. What are those features? Sepal length, sepal width, petal length, petal width. What is the job there? The job is to identify what is the species this iris flower belongs to. Correct? What is the species? And there are 3 species: Virginica, Setosa, and vesicle, right? Someone has to learn the pattern. The output layer does not learn the pattern. Output layer will only tell you whether it is Setosa, Virginica, or what is that? Whatever that, one of those 3, right? The job of the output layer neuron is to give you the final output. It will tell you the final class, but someone has to learn the pattern in the data set. Are you getting my point? Right? So who learns that pattern? The neurons of the hidden layer. That is the job of the neurons of the hidden layer. That is the reason you need the hidden layer. Now the next question is, how do I decide how many neurons to keep in a hidden layer? So this is pretty much a hyperparameter. So people who have come from the data science background know that word. What is a hyperparameter? Anyone? What is a hyperparameter? So hyperparameter is something which you decide as a data scientist or as a subject matter expert, and it is pretty much dependent on your understanding of the problem and your experience. So someone will take 5, someone will take 50, someone will take 500, and there is no correct value to it. That is the meaning of a hyperparameter. So hyperparameter will affect the learning process and the overall performance always, right? So those are hyperparameters. Okay. So for example, in decision trees, the hyperparameter can be set as the max depth, okay, the total number of leaf nodes, the total number of splits, the number of data points per split, the number of data points per leaf, the total number of features to use in a decision tree. So there are so many hyperparameters. If you're talking of a random forest, which is an ensemble algorithm, then the first hyperparameter is how many decision trees you want to collect and make it as a random forest. So by default, that number of estimators itself is a hyperparameter. So I'm just giving analogy from machine learning, okay? The meaning of hyperparameter. So here, the number of neurons in the hidden layer is a hyperparameter. You get to decide. You have to experiment, frankly. Is that clear now? Yes, no, quickly, chat box. Don't use the Q&A unless there is a question there. Okay. Now, is it necessary that I have to have only one hidden layer? Is the next question. Answer is clearly no. The number of hidden layers itself is another hyperparameter. So you are the architecture. You are the architect. Sorry, you are the architect here, and you are designing your own neural network for a specific application. The figure that you see on this slide is called as neural network architecture. You are the architect. So I get to decide how many neurons to use in a hidden layer and how many hidden layers. I can have hundreds of hidden layers, and each hidden layer having hundreds of neurons. So I will decide as per my application. It is as simple as that. One very, very important question. How many neurons to have in the output layer? Who decides that, or what decides that? If you have a pen and paper, please note it down. For a regression problem, you will always have a single neuron in the output layer. It is as simple as that, no questions. What is a regression problem? You need one output for each sample, no? Right? House pricing data set, just imagine what are the features, number of rooms. You remember Boston house pricing data set, okay? Crime rate, proximity to highways, tax paid, percentage of blacks, Charles River dummy variable, and number of, there are 13 variables in that Boston house pricing data set. And finally, you have just one value of that house price, just one value. So why do you need hundreds of neurons in the output layer, right? So you just need one neuron in the output layer for a regression problem. End of the story. No discussions needed. It is as simple as that. Clear? Next is classification problem. Again, if you have a pen and paper, immediately note it down. The number of neurons in the output layer is always equal to the number of classes. So if you have a binary classification, you can have two neurons. Actually as one neuron also, but we do not prefer. We always prefer to have two neurons for a binary classification. And if it is a multi-class, so for example, for the iris data set, we had three classes. We had three classes, correct? So how many neurons will be there in the output layer? Come on, the chat box. 3. Perfect, perfect. So you guys are now clear how to design a neural network. Yes, a basic architecture is clear. Now the next question is, how do I train this network? Next question is, how do I train this network? Okay. Now I'm showing you a fairly complicated diagram. Okay. Maybe I'll just take it in the presentation mode because things will appear one by one. Okay. Okay. Sorry. This is how it goes. Okay. So what are 5.1, 3.5? If you guys remember, I don't expect. Okay. But 5.1 is the value of the sepal length of the first record in the iris data set. 3.5 is actually the value of the sepal width. 1.4 is the petal length and 0.2 is the petal width. Okay, so basically these are your values coming from the data set. Okay, values coming from the data set. It is as simple as that. Fine. So you just take the first record. Maybe I can show you a simple example here. So don't worry, I'll share all the code with you. Okay, I'll directly show you one data set. Okay, this is your crime rate. And so this is a Boston house pricing data set, right? This is a Boston house pricing data set. So there are 13 features. So if you start counting from here till here, LSTAT, there are 13 features. And MEDV, that is your target variable that you have to learn. Okay, so 13 features. So now what I'm saying is the values of the first record will be captured by those input layer nodes. Simple. So I would have 13 nodes in my input layer. In the first pass, in the first iteration, you can say, the first node will capture this value. The second node will capture this value. The third node will capture this value, and so on and so forth. Simple? Yes or no? Come on. Is that making sense? Is that connect there? Perfect. Okay. So let's go back then. Fine. So for simplicity, I have just taken a single hidden layer. For simplicity, I've taken a single hidden layer. Okay, and I have labeled them. Fine. So now as you see, each neuron, now listen to me very carefully. If you have a pen and paper, just note it down. Okay, so each neuron in any layer is fully connected to all the neurons or nodes in the previous layer and all the neurons in the subsequent layer. That is how I have connected. Can you see each neuron here? Sorry, each node here is connected to all the neurons of the hidden layer. And then again, all the neurons of the output layer are connected to all the 3 neurons of the hidden layer. So such a network is called as fully connected network, FCN. This is also called as dense network, DENSE, dense network, or a fully connected network, FCN. What is fully connected? Fully connected means each neuron or node in any layer is fully connected to all the neurons of the previous layer and all the neurons of the subsequent layer. It is that simple. Listen to me, that word dense. I'm just typing it down in the chat box because that's the exact keyword you have to remember. That keyword I'll be using in my code. Perfect, perfect. Okay, now how does the input go? Okay, now let me So X1, X2, X3, X4. So imagine that these are the 4 features, and 1, 2, 3 are the numbering of my neurons in the first hidden layer, and Y1 and Y2 are the 2 outputs. Simple, because there are 2 neurons in the output layer. So obviously those 2 neurons will give 2 outputs, Y1 and Y2, whatever. Till here it is fine. Next is, what are these W's? Now W's are the weights corresponding to each of these connections. Please understand, there is some technical stuff I'm taking time because there is nothing else in the code otherwise. Okay, so this is the only thing that people struggle to understand. Code is all chat GPT. Okay, you just give a prompt, give me a simple neural network which can solve the iris dataset problem. In just 15 seconds, you'll get that entire code. I have just copy pasted that code in my Jupyter notebook. I'll tell you very frankly. So there is no fancy stuff in coding henceforth. Okay, what is more important is to understand what is really going behind the scenes. If that knowledge is what would be evaluated, which will help you perpetually and will help you, the network. Understand? Okay, let me repeat that once again. What are these W's? W's are called as weights. What is weight? Weight is basically attached to each of the connections. So how many connections are there from first layer to the second layer? In the first layer, you have 4 nodes. The second layer you have, or basically the hidden layer, you have 3 neurons. So 4 into 3, simple mathematics will tell you there are 12 connections. How have I named them? W11 means it's weight connecting from the first node to the first neuron. W12 means weight connecting the first node to the second neuron. W31 means the weight connecting the third node to the first neuron. Is that clear? That's how, so it will be a matrix. This weight will be a matrix. Remember that weight will be a matrix. Clear till here? Yes, no? It will be a matrix, okay? Now, each neuron also has, so connections have weights, please understand. These weights are not attached to the neurons. Yes, once again, I repeat this, okay? These weights are not attached to the neurons. Weights are attached to the connections. These bias terms are attached to the neurons. So you have weights and you have biases. So if you have 3 neurons, you'll have 3 bias terms. It is as simple as that. Okay, I have got a very good question, Shubham. So is asking who decides the initial weights? Random initialization. That's what you do in gradient descent. No, it's random initialized, correct? Always. So you can initialize it with zeros. You can randomly initialize with random numbers which follow a uniform distribution, or random initialization which follow a normal distribution. And now we have some sophisticated algorithms, which is Glorot normal, Lee-Kun. So some of these kernel initializers are there. I'll talk about them in my code. It is there in my code. So just wait till I venture into the code. There I'll specifically tell you how to specify these weights initially. By default, if you do not specify, they will be randomly initialized. Is that clear, everyone? Yes, no? Not only the weights, but also the biases will be randomly initialized. Clear? So how many biases you will get? 3 biases for the hidden layer. There is no weight and bias for the input layer. Why? Why there is no weight and bias for the input layer? Because the input layer does not have neurons. Perfect. Now, the next layer, that is basically from the hidden layer to your output layer, those connections will also have weights. So how do I use these weights? I'll tell you that. Okay, just wait. Okay. So those will also have, some weights here. V11 is basically the weight connecting the neuron 1 to the output layer, neuron 1. V21 is basically the weight connecting the second neuron of the hidden layer to the first neuron of the output layer, and so on, basically, right? And then we have the bias terms for the neurons of the output layer, correct? So again, you will get a matrix. So here it is, bias terms are 3 cross 1 and 2 cross 1, and you have the weight matrix like 4x3 and 3x2. So if you want, you can take a snapshot of this, because this is very, very important, and that will help you in the further understanding. Okay. Why is the bias required? So basically, what happens is when you train the neural network, these randomly initialized weights and bias, they will get updated via an algorithm called as backpropagation. Okay. But before I venture into the backpropagation, we'll have to understand how does a forward pass look like. Okay. How does the forward pass work? Okay. And then, so basically, okay, I think, yeah, it is there. Okay. So this is again summarizing the same thing in terms of matrices this time, in terms of matrices. So W matrix represents all the connections from your input layer to the first hidden layer, and V matrix represents all the connections from the hidden layer to the output layer, correct? And then you have the predictions, fine. Now you can see those matrices on your left side, okay? Now, what is the net input? So can you read this? Net input to the first neuron of the first hidden layer. So I'm talking about this. Okay, let me highlight that. Okay, I'm talking about this guy. So this guy gets a weighted sum of inputs. So these weights are multiplied to the actual numbers. So what were the actual numbers? 5.3, 3.1, 1.4, 2 point something, right? So these were the values of x1, x2, x3, and x4. So these were coming from your data set. These were coming from the data set. So these numbers are now multiplied by their corresponding weights. So what you have is a weighted sum of the inputs, not directly the inputs. So the first operation that you have to understand is it is a weighted sum of the inputs, and you are adding the bias term as well. So the bias term will take care of the, I would not say nonlinearity, but basically any gain or shift is there in the overall, after the overall calculation. That's the bias thing, okay? So this is your net input to the first neuron of the output, hidden layer. Okay, now next is this. Clear this. Okay, now this can be summarized in a simple matrix operation like this: W transpose X plus B. Okay, I will not get into the total mathematics, but I can help you this in terms of code as well. Okay, okay. So whatever is the net. Why is this important to understand? Let me just slightly highlight that. Why is this important? Okay, so imagine that you have 100 neurons in the hidden layer, and then you have again 50, 60 neurons in your output layer. Then if you try to do this scalar operation, okay, this is a scalar operation. If you try to do this scalar operation, W1 x1 plus W2 x2 plus W3 x plus and so on till W100 x100, that will be pretty tedious. And this is for one neuron. Then you repeat the same set of operations for the next neuron. And then you repeat the same calculations for the third neuron, for the fourth neuron, for the fifth neuron. That you keep repeating for all the 100 neurons. That manual calculation is extremely tedious and not at all scalable. What is the scalable solution? This matrix operation is a scalable solution, right? So when you do this, you get a net. So all these calculations happen in just one matrix operation. See, this is the power of linear algebra. That's the reason people say you should be really good in linear algebra, right? So this is the matrix operation, and you can verify why this operation works. Okay, you can go through the recording later, and why this works I've already mentioned in terms of dimensions. So now the net output of the hidden layer. Okay, so this should have been off, not to. This is the net input. Okay, and the net output. So this is the hidden layer which is getting this as the input. Fine. So what is the output of that? The output of that is this calculation. The output of that is calculation. So this calculation will be the output. This output. So what is that calculation? If you see, I have used one function called as ReLU here. Can you see here? ReLU function. So what is that ReLU? ReLU is rectified linear unit. So basically what I'm doing is I'm transforming my net input. What is my net input? WX transpose plus B. That is my net input. So I am manipulating that input by using some function, and that function is called as activation function. Why do you need to use that activation function? because your neural networks will otherwise not be able to learn the non-linearities in your data set. So all these activation functions are non-linear functions. I have a list of all these. I can show that quickly before we get back to this slide once again. So jump there. So here you can see there are some other activation functions are there. You can see this is a ReLU activation function, and then you have sigmoid activation function, which goes from 0 to 1. You have softmax activation function, and then you have something like tanh as the activation function, which goes from -1 to +1. And these are non-linear operations. So basically, here the X is your total weighted sum of the inputs. X is the total weighted sum of the inputs. Okay. So you will apply a non-linear activation function so that your neural network is able to learn the non-linearities in your data set. If you do not apply a non-linear activation function, then your entire neural network will be as simple as a linear regression model. It is as simple as a linear regression model, right? Because matrix operation is like what? Multiplying and adding, and that's what you do in your linear regression also. Like, what is your linear regression model? W1x1 plus W2x2 plus W3x3 and so on, right? That's a linear regression. So if you do not apply a non-linear function on that, the net neural network will always remain linear. So you have to use a activation function so that your hidden layers are able to learn the non-linearities, the non-linear patterns in your data set. So this is the simplest way I can put, because I really do not want to get into all the calculations and stuff, but this is the simplest way of explaining. Okay. And then that output goes as input to the output layer. Once again, I repeat, this output will go as, sorry. So this output will go as input. Okay, that output will go as input to the output layer, So this is the net input. Okay, and that input is again transformed by another activation function. Did you notice I have changed the activation function here? It was ReLU and now it is softmax. So that brings to the question, how do I decide which activation function to use in which scenario? I'll give you a clear answer to that. Okay, but again, you have to have your pen and paper ready. Okay, because there is no slide noting that down. Okay, so I'll tell you very clearly in black and white which activation function to use for which kind of problem and for which layer. So it is dependent on the problem that you are solving, number one, and it is further dependent on the layer that you are talking about. So I'll give you a very clear answer to that. Right now, I have just used randomly ReLU and softmax just for the sake of demonstration. Okay, fine. So this final output that you get here, now the last statement before we go to the code. Okay, one last statement before we go to the code. This last output that I get is what we call as a forward pass. Is one forward pass. You feed the data from here. You feed the data from here. It goes to the hidden layer, and then it goes to the output layer, and finally you get some predicted value. That's what your predicted value is here, right? So the moment you get a predicted value, can you see your data is flowing linearly? This is why we call it as a forward pass. I will now show you how to do one forward pass using simple NumPy. Ready? I'll exceed the session. This is typically the case with me. Okay, so maybe another 15-20 minutes, or maybe even 8:30. Okay, I hope you guys are fine with that. Okay. Okay, so I'm clearing all my annotations here and directly jumping to the code part, because I don't want to get into the too much of the mathematics. That will not be very helpful. So now I'm going to tell you, okay, the activation functions. Okay, I'm going to tell you all the activation functions. So if you go to keras.io, sorry. So Keras is a wrapper over TensorFlow, and you can use TensorFlow, you can use Theano, you can use PyTorch, sorry. You can use Cafe, you can use Fast API. So there are 5 most commonly used frameworks to create neural networks. Once again, I repeat, there are 5 most commonly used frameworks to create neural networks. Okay, one is TensorFlow, one is Theano, one is PyTorch, one is Cafe, and one is Fast API. Okay, so these are the 5 most commonly used frameworks. You need a framework to create a neural network. I did not mention the name Keras. Keras is basically a wrapper. At the backend, it can connect with TensorFlow or it can connect with Theano, either of them. Okay, so it's just a wrapper. What does the wrapper mean? So one line of Keras is basically 15 lines of TensorFlow. So I'm not going to teach you TensorFlow, but remember that 15 lines of TensorFlow can be wrapped up into a single line of Keras code. So that Keras makes creating the neural networks, training the neural networks, and visualizing the output ultra simple. Okay, I'll straight away head to the API docs. Yeah, Fast AI. That was just okay. So if you go on the left side here, you can see activation functions. Okay, not there. So I'll just search here. Okay, I'll just search activation, and you'll get all the list of the activation functions which are available. Okay, now you don't have to use all of them. I'll give you a simple example or a simple, yeah. So activation layers. No, not this. Not this. There is a web page which gives you all the list of the, yeah, these are the most commonly used activation layers, but no, not this. I'm looking for the page which has the list of all the activation functions. So do we have it here? Activations, no. Optimizers, losses. It is there, maybe I'm just missing. Okay, so this has a lot of activation functions. Yes, these are the available activations, correct. So ReLU is one of them. And then you have sigmoid, you have softmax, next one, and you have soft plus and so on. So all the equations, see, there are a number of the equations are also given. For each of them, the equations are also given. If you see this documentation page, the equations are also given for each of them. So I have used these equations and I just wanted to create a visualization. How do they look like? Okay, so the first thing is, I just want to visualize. So I have a linear activation. I have ReLU. So linear means what goes in comes out as it is, no processing down. That's a linear activation. Once again, what goes in comes out as it is. See, no processing done. ReLU is rectified linear unit, where the output will be 0 if the input is negative. Once again, I repeat, the output would be 0 if the input is negative. What is the input? Input will be your weighted sum of inputs, right? W1 x1 plus W2 x2 plus and so on. That is the net input on which I'm running my activation function, correct? And it is x, basically, if it is positive. So if the value of x is 10, the output is 10. If the value of x is -2, then the output will be 0, right? Sigmoid, this is the equation. And for tan h, this is the equation. Okay, so fine. I've created some values of x for x-axis, and these are remaining, code for the plotting. So I'm not going to discuss all that. So just have a look at the linear activation. So what goes in comes out. It is as simple as that. ReLU, for all the negative values, can you see? For all the negative values, the output is 0. And if the value of input is positive, the output is exactly the same. So for 2, it is 2. For 3, it is 3. For 4, it is 4, and so on. Coming to the sigmoid, whatever be the input, the output is always capped between 0 to 1. So if the x value is -infinity, then the output would be exactly 0. It is approaching 0, but it will become 0 only at -infinity. Similarly, at +infinity, this will approach to become 1. So all the intermediate inputs, the output will be capped at 0 to 1, right? In the case of tan h, the plot is exactly same, only that this is not from 0 to 1, it is from -1 to +1. That's the only difference, okay? So that's your tan h. So these are the different activation functions. Then the next thing is I would need a loss function. So what is a loss function? Okay. So this is how you would visualize a loss function. Okay, so what is a loss function? I would strongly suggest everyone to go through this article. I'll give you the link of this article. If you go to Analytics Vidhya blog, okay, I'll give you one article. You should read that. Okay, so I'm just going to that blog, and I would want you guys to read one article. So there should be a search button somewhere. Search button. Okay. I skipped it. Yeah, it is there. I'm searching for optimization. So what is optimization? What are optimizers and what are loss functions? All this is very clearly mentioned in this article which I have written. And I have already taken one DataHour on this optimization and the role of optimization in machine learning and deep learning. So we do not have enough scope to discuss about all the optimization here. So that's the reason I'm giving the link of this article. So what are optimizers? What are loss functions? Which loss functions are available? Which loss functions are supposed to be used to solve which kind of problems? Every single thing is discussed in this article. I'm just giving you the link of this article in the chat box. This will help you. So please note this down. Okay. So here you will see a table. So these are the different algorithms and these are the loss functions which is used. So what is a loss function? I'll just tell you in one line. What is a loss function? Loss function is a function which you are trying to minimize while finding the optimal values of the weights and bias. Once again, I repeat, loss function is a function which you want to minimize while finding the optimal values of the weights and the bias. Why do you need to find out the optimal values of the weights and bias? Because random values of the weights and bias will give you random outputs. Please understand that. A neural network where the weights and the bias terms, okay, these all W's and V's, if they are random numbers, the output will also be a random number. So you need these weights and bias to be learned properly. So during the training process, okay, we are trying to find out the optimal values. Please listen to me carefully. We are trying to find out the optimal values, the right values of these weights and bias. Okay, and how do we do that? We do that by minimizing the loss function. That exact statement you will find in this article. Okay, now which loss function is used in which machine learning algorithm? This is the table. There is another table. So loss functions are used everywhere for regression algorithms, for classification algorithms, and you will find one statement here. Please read this. In deep learning, you can create your own neural networks and choose your own loss function. That is the beauty. You can choose your own loss function as per the problem, and all the available loss functions are here. So I'll just click on that link and you can see all the loss functions available here, right? So these are all the possible loss functions, but you don't have to know all of them. You don't have to know all of them because I'll give you a clear idea which loss function to use in what kind of scenario. So I've already committed. I'll tell you which activation function to use when, and now I am also going to help you which loss function to use when. So two things I'm going to help you with. Okay. So, but please help yourself in terms of the optimization, why we are doing, and all that. Okay, so everything is mentioned here very clearly. What is an optimization problem? What is now the third thing is optimizer. There is a third word called as optimizer. What is that optimizer? Now the optimizer is the actual algorithm which is trying to find out the optimal values. So here there is a section called as how do we solve this optimization problem, or there is something called as optimizer. Okay, so that statement will also be there somewhere, right? So I'm just clicking on this link. So these are the available optimizers in deep learning. It's very clearly mentioned here. Okay, there are some advanced optimizers in deep learning. And what is this optimizer? Optimizer is the algorithm which will find the optimal values of the weights and bias by minimizing the loss function. That's the complete statement. Once again, I repeat. Optimizer is the actual algorithm which will find the optimal values of the weights and bias during your training process by minimizing the loss function. Right? So what all optimizers are there? Now you have all the list. Okay. You can see here, Adam, I think here. So these are the available optimizers. You have SGD, that is a stochastic gradient descent. RMS prof. Adam is adaptive momentum, and then ADA delta, ADA grad, ADA max. NADM is your Nesterov accelerated adaptive momentum. Okay, and so on. So I'll not get into all the technical details, but you can experiment with these optimizers. So which optimizer to use for which kind of problem? Now that's pretty much a trial and error. There is no single answer to that. There is no single. You will have to experiment. Okay, which optimizer to use for which kind of problem. But there is a clear answer to choice of loss function and activation function. Right. That is what I'm going to help you with next. Okay. So coming back to my code. So this is how you have your mean square error loss function. Normally, we are going to use the mean square error loss function for a regression problem. And for a, if you want, I can just note that down quickly for you. And I have purposefully not put that in the slide so that I want you guys to note it. Okay. So how do I decide which loss function to use and which activation? So we'll start with the activation functions. Okay. So activation functions. So normally for hidden layers, go for ReLU. Don't waste time in experimenting with a number of things. That is what people have already done in the last 90 years. Don't waste your time. Unless and until you have a very strong reason not to go for ReLU, go for ReLU. It is as simple as that. End of the story. No discussion needed. No questions to be asked. People have figured this out the hard way. This was one of the biggest breakthrough, 2015 by Geoffrey Hinton's group when they came up with this ReLU activation function. So all the hidden layers in all the all the sophisticated hidden layers of every single neural network, you'll find ReLU by default. End of the story. Now coming back to the output layer. Now output layer will depend if it is a regression problem. Go for you can go for ReLU also or linear. Now why do you want to go for ReLU? Suppose your predicted value is a stock price. Now you know that the stock price cannot go negative. So ReLU will never give you a negative output, but linear can give you a negative output. So you have to be clear on that. Okay. So if you can accept negative outputs, then go for linear. And if you cannot accept negative outputs, go for ReLU. End of the story. If you have a classification problem, see, it is that simple. Okay, it is that simple. You just have to remember for classification problem, okay, go for softmax directly. Don't waste time in sigmoid design dial. Directly go for soft. Done. Now coming to so I've already mentioned the number of nodes in the hidden layer. Sorry, number of nodes in the input layer will be equal to the number of features. That's very clear. Similarly, number of neurons, because I'm going to create a network based on these inputs. Okay, neurons in the output layer is equal to 1 for regression problem. Straight away I have already mentioned, and that will be again equal to the number of classes for classification problem. It is as simple as that. Number of neurons in the hidden layer is a hyperparameter, so you can take anything as you want. Fine. Now activation function is done. Loss function. So loss function for regression problem, directly go for MSE, mean square error loss function, or mean absolute error loss function, or there is mean square logarithmic error also. You can experiment with all these, but this is the most common. This is the most common, but there are others also. So go with MSE by default. until and unless you have a strong reason. I'll share this text file, don't worry, mind. Okay, I'll just copy and paste it in the chat box at the end. For a classification problem, okay, the loss function can be taken as binary cross entropy, but I would normally, so if you are taking binary cross entropy BCE, okay, then binary cross entropy, then you must make sure that you have only one neuron in the output layer, and so you have to make sure two things. If you are taking binary cross entropy, okay, for a binary classification, okay, so there are things that you have to make sure. So for binary classification, if you're taking binary cross entropy, so it's already there. I can show you binary cross entropy. You can see the very first one, the binary cross entropy. So this is what I'm talking about. Okay, so if you're taking binary cross entropy, you have to make sure that you have only one neuron in the output layer, and the activation function in that activation function should be equal to sigmoid. Not softmax. Okay, and for same statement I'm repeating. If you're taking a binary classification as two neurons, then you can take categorical cross entropy, CCE. You can take categorical cross entropy. In this case, you have to take two neurons in the output layer, and then you have to use softmax as the activation function and not sigmoid. So you can play with this. The results hardly differ. Okay, the results hardly differ. So I always would go for this for binary classification because I need just one neuron in the output layer, and that neuron will give it a probability. So if the probability is 0.7, which is more than the threshold, the predicted class label would be 1. And if the probability is less than 0.5, the predicted label would be 0. It is as simple as that. Okay. The categorical cross entropy. Can you see the next one? Categorical cross entropy. This is the one I'm talking about. The categorical cross entropy. So for a binary classification, please understand. For a binary classification, you can use categorical cross entropy, but then you have to do a one hot encoding of your output. You have to do one hot encoding of your output. And so you need two neurons in the output layer. And if you have two neurons, then you cannot use sigmoid. You have to go for softmax as the activation function. Finally, for multi-class, we have no choice. This statement will be simply copy-pasted. This will be categorical cross entropy without any doubt. It is as simple as. For multi-class, it will be categorical cross entropy. It is as simple as that. So in a multi-class, I've already mentioned, in a multi-class case, how many neurons you will be having in the output layer equal to the number of classes. Fine. So this is how you can generalize. So I'm just pasting this in the chat box, and let's straight away go towards the code part. So first I will show you how the forward pass can be done in a scalar version. So this will give you a black and white idea about how the neural network is working. Okay. So I'll show you 4 pieces of code. One is for forward pass. One is again for a forward pass, which is in a matrix form. The third one will be a regression problem. It is there in the same notebook. And the fourth one would be a classification problem. So these are pretty simple. So it won't take much time in explaining the codes. Okay. So here, let me. Oh, I'm sorry. So this is just got reversed. This is the scalar version. Just got reversed. This is my vectorized version. So what is the difference? I'll tell you. But let's first see the simpler version. What is the simpler version? So I have the ReLU and I have the sigmoid activation functions ready. Okay. So now I'm going to create a very simple neural network. What neural network am I creating? Let me draw it here. And it will be very clear. So clearly input data has got 3 random numbers. So I need 3 neurons in my input layer. So I'm writing it as input layer. Right? Then I have hidden layer, right? And this hidden layer has 3 weights. Can you see there are 3 weights? So I'll have 3 weights in my hidden layer. And then, okay, sorry. I think I'm taking only one neuron in the hidden layer. And then finally, I'm taking, which color shall I choose? Blue. Okay, so this is my hidden layer. And this is my output layer. Okay, let's put the connections now. Let's put the connections. Okay, so you will see the numbers going in and out. Okay, I'll just join them. So this is my W1. This is my W2. So please, I'm just drawing with my fingers. So please excuse my handwriting. So these are the 3 connections, W1, W2, and W3. And there will be a bias term here. Correct? This is my bias term. Everyone clear till this point? And now there will be one connection here, which is for my W4. So this is my W4. And there is a bias term for this, which is my B2, I think. This is my B1 and this is the B2. And this is the final output I get at the end. This is my final output that I get in the end. Any questions on this neural network that I'm going to discuss? This is the neural network for which code I am giving you right now. So I'm going to give you this code. Okay. This is the neural network that I've got. Yes, everyone is following me. Few people have dropped out, but that's okay. Yeah, so this is the neural network that I have drawn here. Okay. So now I've got my input data. So 3 random numbers I'm getting. So 3 random numbers are coming here, here, and here. These are the 3 random numbers. Okay, these are the 3. So when you download this code, please look at each value one by one, print those values and see. I'm not printing the values because I want all the code to be visible in one screen alongside my network. That's the reason I'm not printing all the outputs, right? So please excuse me on that part. So this is clear. So what is W1, W2, W3 is clear. What is B1? That is also clear. This is clear. This is clear. I'm just putting a checkbox. Check. So W4 is clear. Where is it? B2 is also clear. Where is it? So did you see? I'm just randomly initializing everything. Perfect. Perfect. Now comes the main thing. Let me scroll up slightly. Okay. And let me erase some of the things here so that I can make things simple. Okay. I'm just scrolling up slightly. Can you see here what I have written? What is the weighted sum? Okay, I'll take it. So what is the weighted sum which goes to the hidden layer? That is input data 0. So what is input data 0? This is my input data 0, correct? This is my 0. I'll just write it down. This is 0. This is 0. This is 1 and 2, correct? So this 0 is multiplied by W1. 1 is multiplied by W2. This 1 is multiplied by W2. And this 2 is multiplied by W3. And the B1 is added to that. That will be the total input which goes to the hidden layer. That's exactly what I was trying to tell you. Any questions? What did I do with that input? I applied an activation function. So this is the net input which goes to the, this is the net input which goes to the hidden layer. On that net input, I applied a activation function, and then the output came out. So this is the output of the hidden layer. So this is the output of the hidden layer. Now that output is multiplied with W. So this output is multiplied with W4, and the bias term is added to that. The bias term is added to that, and you get the net input to the hidden layer. Sorry, output layer. You get the net input to the. So this output is the weighted output. This weighted output will become the input to the output layer. This will become input to the output layer. And then you apply another activation function and you get a final output. So this final output is here. So every time you run this code, you will get a different value because everything is randomly initialized. Okay. So don't worry. So can I clear my screen? Can I clear my screen? Yeah. So every time I run this code, I'll get a different value for the reason all these numbers are randomly initialized. But is there any gap in the understanding here? Come on. What I have done here is the same operation, but in terms of matrix operation. Can you see? So let me show you that matrix operation. So input data is your X, weights, this is your W, this is your capital B, this is your V, and this is your C. Now what did I do? NP dot, this is a matrix multiplication. So you are multiplying input X with weights W. So it's X transpose, and then you are adding the bias one. So bias, so this is row, this that line number 1 forward pass. Of that forward pass. So this becomes the output. That output goes as the input here. Can you see? On that input, so let's say this value is H1. That H1 is now multiplied with weights 2. What is weights 2? Your V. And then adding another bias, which is your C. This becomes your net output of your hidden layer, which goes as input to the output layer. So that is final return. That is final return in the forward pass. So it is as simple as that. So here, these entire operations that we were performing in multiple lines of code is just performed in one line by use of matrix multiplication, forward pass function, and directly I'm getting the output. It is simple. Okay, so let's go ahead and create an actual neural network. Okay, now what this neural network is. Okay, so how am I creating? By using the TensorFlow Keras sequential. Why is it sequential? Because my data is going to flow in one direction. And why is it dense? Because I'm going to use fully connected layers, right? Okay, so how is the network? So this is my input layer. How do I know that this is my input layer? Can you see the input shape here? Input shape 1. So basically, I'm creating X values here somewhere up. I can show you. Yeah, it is there up. So it has got 3 values just now I have discussed. So, and then this is a first hidden layer. Okay, this is my first hidden layer. This is my first hidden layer. So, oh, sorry. Let me draw this once again. So this is my first hidden layer with 3. And then the next hidden layer is again this 3. And I have final output layer as 1. So this is my HL1. This is HL2. This is the output layer. And then there are 3 input nodes, or whatever be the number of input nodes, it is given here. So 1, 2, 3, that is given out by this. Okay, so that is determined by this, the input shape. Fine. I am applying the activation function ReLU here. This is the activation function ReLU here once again. And here by default, again, a linear activation function is being used because I haven't mentioned anything. Okay. Fine. Now, how do I calculate the number of parameters? That is very simple. So this is the network and everything is connected to everyone. Okay. That's why it is called fully connected network. This is connected to this, and this is all fine. So this is a fully connected network. Okay, let's clear this. Now, how do I calculate these parameters? That's very simple. So here you had 3 neurons in the hidden layer 1. Or let me take a single value. Okay, here and a simple single value in the output. So this is my output, right? Fine. So this is my hidden layer 1, hidden layer 2, and this is my output layer. Fine. So now you will have one layer of weights. Okay, you'll have one layer of weights here, another layer of weights here, and another layer of weights here, right? So that is why we have these numbers. And not just the weights, it is the bias also being calculated or being added there. Okay. So this 6 is not just the number of weights, but also includes the number of bias terms. Correct. So this 6 is coming because of the total weights and bias of the first hidden layer. This is the weights and bias of the second hidden layer. And this is the total weights and bias for the output layer. There's nothing in the input layer. So there is no parameter attached to it. So total I have got 22 parameters and then I can train. Oh, sorry. Perfect. So this is how I create my neural network. I am just adding, can you see the code? I'm just adding the layers one by one in sequence. So add one dense layer with 3 neurons, then add another dense layer with another 3 neurons, and finally add the last layer. Last layer is always the output layer. You never add anything for the input layer because input layer does not have neurons. So input layer is never added. Remember this. So when I summarize the model, this is my neural network model. This is how it comes up. Okay. This is a summary which will give you the total number of parameters, and then we can train this. Now, this was just a dummy network. Now, let me take a real problem and create a neural network and train. It is as simple, right? So everyone is aware of the Boston house pricing data set. I don't have to mention that. So I'm just loading that data from TensorFlow data sets. This is my data set, I guess. And then I have 506 rows and 14 columns, which includes the MEDV column, which is your median value of the house price. Okay, so these are the features: the crime rate in that locality, the percentage of land zoned as green, industrialization index, Charles River dummy variable, the nitric oxide concentration in that locality, the average number of rooms per dwelling, this is the average age of the houses in that locality, this is the average distance of that locality from the 5 employment hubs in Boston. This is the radial accessibility index of that locality from the highways. This is the average tax paid by the people in that locality. This is the people to teacher ratio in that locality. This is the number of blacks residing in that locality. This is the percentage of lower status of population in that locality. So based on these 13 inputs, I have to predict the median value of the house price. So 24 means $24,000. Remember that. I've probably mentioned that somewhere. 24 is $1,000. Okay. So the objective is to predict the median value of the house price given the features. So I think I have decently explained the project here, right? So all these are numeric data. You can very well see. The first thing is, of course, in any machine learning or deep learning project, you would do a test train split, no fancy stuff. So test train split. And then you see that I have done a 2080. So the test size is 20%. So the training size would be 80%. 80% is the data on which you will train your neural network. 20% is where you will test the neural network. Okay, good. So these are the number of rows or samples in your training data, and this is the number of samples in your test data. I'm just showing you these values in the training set. Why am I showing that? Because you can see that there are the ranges are quite different. So neural network will get into serious trouble if the range of the values are quite different. You see this range, these values are in decimals, whereas these values are in hundreds. Okay, and these values are also in tens and even hundreds here. Okay, but that's a big problem for a neural network. So what is the first thing that I do here? I'll do a scaling operation, right? I did a scaling operation. So let me show you that in the next line of code. I did a standard scaler, and just to verify, so you do a fit transform on the training set and you just transform your test set. Okay, so this is all standard knowledge base. Even coming from the data science background will know this. So see the values after standardization, none of these values are in the range of hundreds or tens. All the values are few minus to few plus. -1, -2, 2 + 1 + 2. That's the narrow range in which all the values are scaled. So this is the values after scaling, and these are the first 5 rows before scaling. Good. So everyone with me here, maybe I'll take some questions. I did not look at the chat box for long. Let me give a quick pause here, because next thing is we are going to create the model. Next thing is we are going to create the model and then we are going to train it, right? Fine. I'm being given reminders by the moderator to close. Maybe I'll take another 5-10 minutes, not more. Okay, it's only about the project part which is remaining. So I hope that is fine with everyone. Okay, good. So now what did I do? I am creating the first hidden layer with 64 neurons. Activation function is ReLU. And the input shape is X-train shape 1. So what is this X-train shape 1? This will give me 404. Sorry. This is 0, this is 1, 13. It will give me 13, right? So the second. So I'm taking the shape, and when you take the shape, the first element, that is 0th index, will have the number of rows, and the first index will have the number of columns. So the number of columns will be the number of features, as we have said, and that is the number of nodes in your input layer. So input layer is automatically inferred. Please note this. The input layer is automatically inferred. You do not explicitly create an input layer. So this first layer itself is your first hidden layer. This is your second hidden layer. And since this is a regression problem, I have one neuron in the output layer. Any questions here? Any questions on this neural network? Perfect. So let me summarize this. Now, there is a fantastic way to visualize this neural network also. So if you want, I can just tell you how these numbers came in. Okay. Ready? I can tell you these numbers, how it came in. So there are 13 input nodes. Please listen to me very carefully. There are 13 input nodes. And in the first hidden layer, I have got 64 neurons. So 13 into 64 is the total number of connections. Please, clear? And then there is 64 neurons. So there will be 64 bias terms. Awesome. You see, this number 896 matches exactly. Now you are clear how these 896 parameters are coming. So 13 features in the input layer multiplied by 64 neurons in the first hidden layer. That is the total number of connections. So weights. So how many weights you have? This is the total number of weights. How many bias terms? The number of bias terms will be equal to the number of neurons. 64 neurons. So 64 bias terms added together is your total number of parameters. How do I get 2080? Okay. I'll give you that. So there are connections from 64 neurons to 32 neurons, correct? 64 neurons connecting to 32 neurons and then 32 bias terms. Perfect. 2080. It is that simple. It is that simple, my dear. If you have that level of clarity, no one can actually confuse you. Isn't it? Isn't it? It's that simple. And now, can you guys tell me what calculation will give me 33? Come on, use your chat box and tell me what calculation will give you 33. How did you get this last 33? I have already mentioned that. That's a hyperparameter. So no one decides 64 or 32. You will decide. You will experiment. You will just experiment. Normally we take these numbers as multiples of 8 for obvious computational reasons. Okay. These normally we take as multiples of 8. So either 8 or 16 or 32 or 64 or 128 or 256 and so on and so forth. Right. This is hyperparameter and you can tune that. Hari, yes, absolutely. That's hyperparameter tuning. You can tune that also. So we have 32 neurons in the second hidden layer connecting to one neuron of the output layer plus one bias term of the output layer. Correct? Perfect. That's how you get 33. Add them, you'll get how many parameters to be trained? 3009 parameters to be trained. Awesome. Someone has asked, did you get the target variable in the split? Yes, that has to be there. No, there's a supervised learning problem, so there has to be the target variable. So can you see this? Y train and Y test. It is there. It has to be there. Okay, so let's go ahead and train this. I've already trained it, so I'll directly show you the output. So this is another way you can visualize your neural network. I'll just zoom out slightly. So can you see? Input is 13 features that connects to 64 neurons of the first hidden layer. Now that 64 connects to 32 neurons of the second hidden layer, and that 32 neurons of the second hidden layer connects to one neuron of the output layer. And that's how you get the data flowing in a sequence. That is why it is a sequential model. Perfect. So just use that piece of code. You will need to install PyDot and GraphBase. So that installation code is there somewhere. Okay, PyDot and PyDot and GraphBase. You need to install. So pip install is there somewhere. Yeah, I have done that. Okay, so you will have to install this. That's the only thing. These are additional things. So yeah, some of the things are now getting embedded within TensorFlow. True. Okay, fine. So let's get back. So I have trained this. So how do you train this? Before you train, you have to compile. So while compiling, you'll have to mention at least two things. There are three things for a classification, but at least two things for regression. So which two things? How you are going to minimize your loss function? Which loss function are you going to minimize? Which loss function are you going to minimize? Which loss function are you going to minimize for a regression problem, my dear? You are going to minimize the mean square error loss function. Yes, you are going to minimize the mean square error loss function, right? So this is the link for the Jupyter notebook. You guys can download this. So how do you minimize that algorithm? You can choose Adam, NADM, RMS prop, SGD, whatever. So you compile the network. Compilation means you are making the network ready. You are making the network ready. You are just mentally preparing. And the actual training starts here. Here you have to provide your training data, X train and Y train, because it's a supervised learning problem. And then how many epochs you want to train and what is the batch size. So this is a mini batch gradient descent kind of. Okay, this is all mini batch gradient descent. And what is the validation split here? So out of that 80% of the training set. So this is already 80%, right? Of the overall data set. So 10% of this will be used for validation. Okay, why do we need the validation? Otherwise, we will never be able to figure out whether your neural network is overfitting. I've just shared the link for the GitHub. Okay, I've just shared the GitHub link. I think I'm sharing it with the host only. So now I'm sharing it with everyone. So you can just copy. So I think these parameters are very clear, correct? How many epochs you are going to train? How many batch size? So what is the batch size? Basically, after every 32 samples, I'm going to update my weights. I'm not going to update my weight after every sample. Okay, I've got 402 samples. So I'm not going to update my weight for all the 402 samples per epoch. Okay, I'm going to update my weights in batches of 32. So for 32 samples, I'll collect all the error terms. And those error terms will be used to update the weights via back-propagation algorithm, which I have not discussed in the interest of time. And then I'm using my validation split to check. So here you can see how many milliseconds per step it has taken. What is the value of the loss function in the training set? And this is the value of the loss function for the test set. Okay, so let's go ahead. In the interest of time, I'm not executing this because this might take some time. So I've got my final model. So final model has got this as the loss function value, and this is the loss function value for the validation set. Now let me evaluate my model in the test set, and then let me print the output. So this is the value of the loss function. This is the value of the loss function in the test set, right? But how do I know how good or bad it is? Okay, so I'm plotting the progress of the training, okay, which is training loss and validation loss. So the blue one is the training loss and the orange one is the validation loss. You can see that there is hardly any improvement after 20th epoch. So why is this plot needed? This plot is needed to help you understand that nothing much happened after this. So what do? The next time when you train the model, you can cut short it to 20 or 25 epochs. That's it. You don't need 100 epochs. Essentially in 20 epochs, whatever it could learn, it has already learned. So you don't need to go to 100 epochs because there is hardly anything happening down the line, right? So this plot can help you to decide how many epochs is actually needed, right? Now let's directly go to another classification problem. This is again very well-known data set, wine quality classification problem. This is already available in scikit-learn also. Okay, so what is this? I'll just read out this. Contains information about the chemical composition of the wines from 3 different parts of Italy. And then the data set has got 13 features once again, which includes alcohol content, malic acid content, flavonoids, non-flavonoids, color intensity, and all that stuff. Finally, we have to classify what is the quality of that wine. 1, 2, or 3. 1 means the best quality, 3rd means the worst quality of wine. Fine. So it's a classification problem. The big reason by which I've taken this particular data set is I didn't want to spend time in encoding, missing value treatment, EDA, and all that stuff, right? Those things you know what to do. So let me directly come to the data set. You can see alcohol, malic acid content, ash content, alkalinity, magnesium, flavonoids, non-flavonoids, procyanins, and so on. So based on all that, we have to classify whether what is the class of that wine. So you can see 0, 1, and 2. These are the three classes, 0, 1, and 2. Okay. So again, you can see there are 178 rows and 14 columns. The 14th column is my target variable. Again, as usual, I am doing a test train split. While doing a test train split, I'm dropping the class from the X and I'm using that class for the Y. I'm having 80-20 split as usual. So this part of the code is very clear. So 142 rows will go in the training set and 36 rows will go in the test set. 13 features in total. So this is simple. Again, as usual, I am scaling the data set. You can see. And after that, I'm doing a one-hot encoding because this is a multi-class problem. So for a multi-class problem, you have to do a one-hot encoding of your target variable. So 0, 1, 2. So you can see here. So please pay attention here. This is something new which we have not seen till now. This is the value of Y. This is your target class. This is the value of your target class. Okay. This is what is there in your original data set. Now I'm going to do a one-hot encoding, and as a result, the one-hot encoded values I'm going to show you is this. So I'm using this function for one-hot encoding. I'm using this function for one-hot encoding, and after one-hot encoding, the same Y is now split into 3 columns. That is the result of one-hot encoding. So if you don't know what is one-hot encoding, that's pretty much a standard knowledge base in data science machine learning. So we will not get into that discussion or ask ChatGPT what is one-hot encoding. Okay. So basically, one column of your target is now converted into n number of columns where n is equal to the number of classes. So if there are 50 classes, that one single Y will convert into 50 columns of Y. Simple, right? So now this architecture is very same. I just copy and paste it from there. Only one difference that I have done here is softmax. Okay, this is the only difference that I have done. The first hidden layer is 64 neurons, second hidden layer is 32 neurons, and the second difference is instead of 1, I have 3 here. Why 3? Because there are 3 output variables. Okay, there are 3 classes. Sorry, there are 3 classes. So you need 3 neurons to be able to predict. So what is 001? 001 means it is belonging to the second class. 0, 1, and 2. 0, 1, and 2. Okay. So this one here means it is belonging to the first class. This one here, this is belonging to the second class. And one at the third position is belonging to the third class. So 1, 2, 3 or 0, 1, 2, whatever way you want to spell it out. So these are the 2 key differences as you notice. So 3 neurons in the output layer and softmax as in the activation function, because that is what I have clearly mentioned for a multi-class classification problem. As usual, I have my summary. You can easily go ahead and calculate these parameters. There is no fancy stuff. Okay, it's exactly same as previous. Total number of parameters in this case is 3075. I have just plotted the model just like I did earlier. And then 2 key differences I have. Number 1, instead of mean square error, this time I have got categorical cross entropy. Correct? Second difference here is the matrix was not mentioned earlier. You could have mentioned R square also in the matrix. In the previous case, I did not mention the matrix. So it gave everything in terms of loss function. You can actually mention R square as the metric there. Here I'm using simple accuracy. The total number of correctly classified data points divided by the total number of data points will give you the accuracy. This line is same, copy paste. There's no change in this. Okay, so this is exactly same. 100 epochs, 32 as the batch size, validation split 10%. Perfect. Optimizer, you can experiment. As I said, this is experimentation. No one can tell you which optimizer to use for what kind of problem. No one, not even ChatGPT. You'll have to experiment. So after running for these 100 epochs, these are the results. So let me show you the result. Okay. Same, I'm evaluating my model. So can I look at the last line here? So this is the value of the categorical cross entropy loss function. This is the value of the categorical cross entropy loss function in the training set. This is the accuracy. So 100% is the accuracy of the training set. Validation loss. So this is the value of the loss function in the validation set. And the accuracy in the validation set is also 100%. So somewhere, I think I have created a very good neural network, which is giving me 100% accuracy in the validation set and also 100% accuracy in the test set. Let's see the plots here. You can see very well the training accuracy and the validation accuracy are becoming 100% after roughly 30 to 40 epochs. So you can actually stop your training in 40 epochs if you want, because there is hardly anything happening after 40 epochs. Same way, if you want to plot the loss function, just like before, you can see that both guys are increasing, decreasing, and finally merging. So there is still something happening here. As long as they are, converging, you can continue. But again, this has become very much flat after 40 epochs. Can you see? It has become almost flat after 40 epochs. So if you want, you can stop after 40 epochs. And that is very clearly seen in terms of accuracy also. After 40 epochs, there is no improvement in the accuracy because both the accuracies have become 100%. Okay, so quickly looking at the classification report, since this is a classification problem, so it is very much mandatory to look at the classification report. You can see the precision, you can see the recall, F1 score. And since this is a classification problem, here we have a look at the confusion matrix. And I am not explaining this because I am assuming again, and again I have said that you are coming from a machine learning or data science background. So you already know what is confusion matrix and precision, recall, and F1 scores. Because that is beyond this session. We have already taken n number of data sessions on this classification metrics. At least I remember 8 to 9 sessions we have taken only on classification metrics, only on explaining classification metrics. So please go through the previous data sessions. It's all there in the YouTube channel. Just search for classification metrics and you'll get enough number of explanations and interpretations for this. Now, this last part, in the interest of time, I'm skipping, but what am I doing here? I'll just tell you in 1 minute, this last 1 minute, please allow me, okay? So what I've done here is, till now I have been using random initialization, if you remember, right? This time I'm going to use initialization with zeros. I've mentioned what is kernel initializer. Kernel initializer will initialize the weights by zeros, and bias initializer will initialize all the bias terms with zeros. If you do not use the initializer, then everything will be randomly initialized. That's what has been happening till now. This time I'm initializing all my weights and bias terms with zeros specifically. And then let me summarize the model. It's the same. And then train the model. Okay. So what is this model doing? This model is trying to learn how to find the natural logarithm of a number. So what is the input? Input is x from 1 to 10 in the step size of 1000. Okay, sorry, step size of 0.001. Okay, so I am generating 1000 numbers between 1 and 10, uniformly distributed. Okay, uniformly distributed numbers from 1 to 10, and total number of numbers I have generated is 1000. And y is the natural logarithm of this x. I want my neural network to learn how to find out the logarithm of this x. I'm not going to tell that the y is log of x. It has to learn that y is log of x. Let's see if it is able to do that. I'll execute this and show you. So rest all code is same, compilation, model fitting, and finally, let me plot the predicted value and the actual value, of course. Run, and you see that box. Oh, sorry. Box, and you see that my model's output is pathetic. This is what my model has learned. So this is the output coming from my model. I'll tell you a reason. I'll tell you a reason for this. Okay. This is a non-linear function. This is a non-linear function, and you are using a linear activation. That is the root cause. That is the root cause. So what I'll do is just go up and change the ReLU to maybe sigmoid NC. Okay. See, this is the change that I've done. So I told you sometime back very clearly that you should be using ReLU in the hidden layers until and unless you have a very strong reason. Now I'm presenting that strong reason right now. Okay. So I'll just run this code once again. Yeah, it is done. So let it train for 200 epochs. That will finish very fast because there's a very simple problem. 65, 70, let that finish. And this time you will see the difference. So that is why, training the neural network itself is a skill. It's an art that you learn by enough experimentations. I mean, unless and until you play with your code, we spend enough time with your code, things will be different. Okay. So let me show you. Perfect. It is not able to catch everything, but at least to some extent, it is able to catch the pattern. Initially, it was flat. It was not learning anything. It was completely absurd model. Now this model is at least decent enough. And if you remember, sigmoid is this way, and that's why the outputs are that way, you see. But it is able to at least capture, you see, it is able to modulate to the output. Initially, it was not at all able to capture the pattern because the pattern was non-linear and you are using linear activations, you see. So, and this line of code is doing what? This is the beauty of the today's session, okay? I'm going to show you how to extract the weights and bias of each of those layers after the training is finished. Initially, it was all zeros. You remember, I have clearly mentioned in my code, right? Initially, everything was zeros. Yes, initially, everything was zeros. You can see here, everything is zero. All weights and bias are zero. But at the end of the training, 200 epochs, what are the weights and bias? How do those numbers look like? That's exactly what I'm showing you right now. So the first layer, these are the weights and these are the biases. So 3 neurons in the first layer, okay? And then you have another layer of neurons, second hidden layer, which is having another 3. So 3 cross 3 will be a matrix of 9. So first one is 1 cross 3. This is a 1 cross 3. And there will be 3 bias terms because there are 3 neurons in the first hidden layer. Now between the first hidden layer and the second hidden layer, you have how many connections? 9 connections, 3 into 3. So this is the weights for all the 9 connections. All of them are equal, but of course they are non-zeros. And these are the bias terms for all the 3 neurons of the second hidden layer. And this is the weight for the second hidden layer to the output layer, right? So 3 cross 1. And then finally, this is the bias term of the output. Thank you so much. So you can
Thanks a
download
lot,
this code.
Prashant.
Yeah. So any questions? Let me just quickly check.
Yeah,
the chat. Mostly
yes,
I've taken all the questions, I think. But if there is any question which needs to be addressed, let me have a quick look, because I have taken most of the questions. If there is any question which you want me to discuss, please put that in the chat box. Otherwise, I'm done for this session today.
There are some questions in Q&A section. You can refer to that as well.
Okay. So Sylvia is asking, what is the data requirement for DL huge compared? Why? Because see, deep learning is going to learn the important features and the pattern in the features. Okay. Normally in machine learning, you will handpick the features. There is a feature selection involved in machine learning. There is no feature selection involved in deep learning. So since you are not helping the model is expected to learn all the important features on its own. So for that reason, it needs huge amount of data. Some anonymous attendee has asked what happens when the number of neurons in the hidden layer is more. You'll get more number of parameters. It takes more time for training. Simple. Boston code does have the node values need to be normalized. I have done that. Okay. How the value of the base is decided? Which base? Ashwin, I'm not getting your question. There's one question during the data processing. It is a must for the data to be normalized. For neural networks, yes. For neural networks, yes. For neural networks, yes. I've repeated that 3 times. So please remember that. That's a very much mandatory step. Either you do a standard scalar or you do a min-max scalar, but data has to be normalized. Otherwise, the neurons can give you exploding gradients or what we call as vanishing gradients. Okay, we will not get into all that discussion, but there are some serious issues during weights updations if the data is not normalized. That's a strong reason. How can you use Keras for GPU? Normally, I use PyTorch for GPU codes, not Keras. Okay, so almost everyone who uses GPU by default uses Keras, sorry, PyTorch, unless and until you are working with Google Colab platform. Okay, so that's more intuitive and user friendly. Someone has asked if it is a binary classification, can one use sigmoid active? Yes, I told you, you can use sigmoid, but for that you need to have one output layer neuron. If you are doing one hot encoding for a binary classification, then you will have to go back to softmax. That's clear. How to model, decide bias value? So see, no one is deciding the bias value. The bias value is learned during the backpropagation algorithm, during the weights updation. Dinesh, that was your question. Ashwin is asking one question is difference between matrix multiplication and dot product. They are same. Matrix multiplication and dot is same. Okay. So when you say dot product as in physics, they are different. But the NP dot function is doing a matrix multiplication. Please do not get confused. The NP dot function's output is same as there is a macmul function in the linear algebra module, NP dot linalg dot macmul. So you can use the macmul function for matrix multiplication, or you can use the NP dot function for matrix multiplication. Both are doing the matrix multiplication. Dot product as a word is different from matrix multiplication. So do not get confused. But the function dot does matrix multiplication and not dot product. Okay, Dinesh has asked why fit transform on the training set and only transform. That's the standard knowledge base in the data science thing. See, we do not want to leak information about the test set while doing the modeling. And that's the reason we are only transforming the test set based on learning that we are getting from the training set. So fit means learning. Fit always means learning. When you do a model.fit, so model is learning. So fit transform has to be done on the training set because you have to learn something from the training set. And you don't want to learn anything from the test set. So you just have to transform the test set. You never do a fit transform on a test set. That's a cardinal sin. I'll tell you that is a sin, biggest sin you can ever imagine in data science. Okay, so don't ever do that mistake, not even in the wildest of your dreams. Okay, never do a fit transform on the test set. What is the need for seed? That is to fix the randomness in the random number generators so that you can have consistency of outputs. So the same output gets to you every time you run the same code. Otherwise, if you don't fix the seed, every time you run the same code, you will get a different output because of the random initialization of those weights. So once you fix the seed, all these randomness is gone. And Ruchita has asked, are these weights same in a single layer? So the concept is very much the same. Okay. Natarajan is asking, the last question I get in the chat box, sorry, in the Q&A section is this. In the case of imbalance classification, where do the neural network? So for imbalance, again, you have to do a class balance before you venture into the modeling process. The neural network is a part of modeling. Before modeling, you have to get your data right. So you will probably use a package like IMB learn. There's a algorithm called as the SMOT synthetic minority oversampling technique. So you use some sort of oversampling technique or undersampling techniques to get balance in your data set. Once you have a right balance in your data set, then normalize it, standardize it, and then you feed it to your neural network. Okay. So neural network is part of the modeling, but initial data processing is still needed. Only thing that you do not do in neural networks case is feature selection. Feature selection is never needed, but feature selection is a very, very important part in a standard machine learning algorithm, right? So that is how ML is different slightly from your DL. Rest, ChatGPT can answer you. But I'm telling you the biggest difference between ML and DL. Okay. So anything else, guys, I can help you with? I have already given you the link for this GitHub. If you want, I can just paste that once again for everyone's reference. So you can download all the codes. I'm using a cloud platform, no doubt, but you can configure your machine for, because I did not want to get into the installation and stuff. So directly I am using cloud platform. You can use Google Colab, which is free. So you don't have to pay for this cloud. Just download this Jupyter notebook, upload it into your Google account, and directly right click and open it in Google Colab. That's it. So this is the notebook, and these are the PNG files which were corresponding to those modules. So this is the folder. You can directly download that folder. Okay. Fine. And you guys can connect with me. My LinkedIn profile link, moderator can share once again. Let me unshare my screen. I'll be happy to connect with you guys who have been patient for more than 2 hours now. So I would definitely want to meet you guys who are patient enough to, deal me for 2 hours. Okay, I know that you guys are seriously interested in learning. I completely appreciate your efforts and patience. I'm there to help you out. So please connect with me. And if you have any questions, you can always reach out to me on my LinkedIn, inbox.